Alright, hello everybody. So this is going to be our fourth electronic fundamentals workshop. This time we're going to be talking about OpAmps, which I very briefly introduced at the end of the last meeting. So before we get started, I just want to do a quick review of kind of the components we've already talked about, just to make sure everyone's keeping that fresh in their minds and to really keep it up with the repetition that will hopefully cement these things in your brain. We have, during this time, we've been treating basically our equivalent of voltage is a difference in pressure, and our equivalent of current, electron flow, is using the flow of water. So we'll just write that up here right fast, kind of. Pressure is voltage. Flow, I don't even, I guess I'll just call it F, whatever. Voltage. Flow rate, which isn't generally represented by F, but whatever, it doesn't matter, this is not a formal class. So far we've talked about how resistors, which are schematically this, are basically the equivalent of a narrowing of a pipe. They lower your pressure, they restrict your current. So we've also talked about capacitors, which we kind of compare to basically like a bag, that if you have a pipe going into a bag, you can pull it, you can apply a whole bunch of pressure and fill that bag or that balloon up with a whole bunch of water and or electrons, but there is a finite amount of water or electrons you can kind of store in there. And with this type of thing, it's kind of like the other side of the bag, it's like displacing things. So you're also kind of like, you can push a bunch of electrons in, a bunch of electrons will come out, eventually it stops. This is not an actual path for current, right? You cannot produce flow through a balloon. That doesn't make sense. And then we have inductors. And inductors are basically a flywheel, is like we talked about. So they resist a change in current. When you originally begin to send water through the system, it's like riding a little turbine that's spinning up a flywheel. So you're storing energy by having this mass that you're you push the water through, it spins faster, spins faster. Now when you're at a constant steady state kind of process, it's spinning, you're not really losing energy and keeping it going except for the slightest amount. And if for some reason flow stops, it will then continue to push through the stuff until it slows down. Then we talked about diodes. So diodes are basically mechanical equivalent of check valves, but again, I recognize that probably not a lot of people out there with a whole bunch of fancy valves at home. So what you kind of need to remember for that is they just allow current to flow in one direction. And a check valve is basically like a little thing where there's a big old flapper right here, right? It can only be pushed open this way. So it allows current to go through only in one direction, and it takes a little bit of pressure to keep this open. So in electrical equivalence, current is in one direction, and you have a small voltage drop across it. We also explored some fancier applications of diodes. And then the last thing we talked about were transistors, of which there are kind of two major types. We talked about MOSFETs being the most common one, and that MOSFETs are basically for all intents and purposes, they're not good at throttling. They're basically good at and throttling in this context mean, basically you're not finely controlling it, you're not finely tuning it, it's all or nothing in most cases. And then we talked a little bit about bipolar junction transistors. Where these are good at throttling, but they have some other somewhat less desirable characteristics. These ones, there is actually I drew this wrong. These ones are field effect transistors, so your input voltage, the one that determines whether or not current is allowed to flow through this. Because there's not an actual connection here, it has theoretically infinite impedance. And impedance is like a fancy version of resistance that has some other stuff incorporated with it that's not really important to this. but what you should take away from that is like you can have a signal which doesn't require current. It is voltage driven. For bipolar junction transistors, you do have a path for current. Current is actually what controls the throttling. So that's the important part to get out of that. With that, we briefly showed an internal diagram of OpAmps. They have a whole lot of those bipolar junction transistors. The mechanical equivalent to them, which there aren't any really good, I was able to find that many good pictures of this online, so I just MS Paint doodled my own. They're mechanically equivalent to a dual hydraulically operated, so being driven by water, throttle valve. So what that should mean to you in your head is we are taking water from somewhere, we are using it to control another valve. In like high pressure, like in nuclear operations, this is actually very commonly used because you can take a small signal and use it to have a much larger effect. You can take like a tiny amount of sensed or detected pressure somewhere and say, great, I want to drive a watt flow with that, which is exactly what an op-amp does. So the output for a basic op-amp is proportional to the input. There is some amount of gain is the term used for these. You may have heard that term like used with amplifiers before. That basically they can be used to, it's basically multiplicative, right? So the output voltage is equal to the gain times what is called the non-inverting terminal. If you hear non-inverting, just think plus, or I can just call it like the plus, but it's a little confusing. Minus the V minus. So technically, op-amps are sort of a subcategory of differential amplifiers. It amplifies a difference. Differential amplifiers. That's the breakdown of that phrase. Everybody just usually calls all of them op-amps because for all intents and purposes, most people don't really make differential amplifiers. They usually just make op-amps, and we'll get into that a little bit later why. And these are much like MOSFETs. They are operated by applying a voltage. The voltage that we care about here are these two voltages. In a theoretical op-amp, there is infinite impedance, once again, from these lines and to these. So the mechanical equivalent here, basically what we have is, and hopefully this kind of makes sense, if you have your positive and your negative applied voltages, your applied pressures, if this pressure is higher than this pressure, which way is this going to shift? Anybody? Yes. So this is going to shift left. So when you have a positive voltage that is greater, if your non-inverting terminal has a higher voltage than your inverting terminal, the mechanical equivalent is this little thing is going to slide over, and it's going to allow a whole bunch of this positive supply. You'll see this in various documentation. This is sometimes VCC, this is sometimes VSS, this is a couple different things. But the important thing to know is like this is your positive supply voltage. And if this was closer to the middle, it'd be kind of, I didn't draw this super well, but if it was in the middle, it'd be doing meters, sort of, or kind of both. It's a little abstract, but by lining it up purely to this, you're just fully allowing flow as much as possible through here. And you can get a whole bunch of current at some amplification, right, based on this. So like, this may only be like 5 volts or 5 pounds of pressure and 0 or 1 pound of pressure. This could be like 10,000 pounds. You could have some like actually high pressure hydraulic oil being used to drive something else, but maybe you need a lot of it or something. Or it could be vice versa. Maybe you have a hydraulic pressure that you just need a lower but linearly correlated kind of percentage of. The same is true as if you have the negative, the inverting terminal. If this is a higher pressure than the non-inverting terminal, this is going to shift to the right. Now we're seeing pressure from this, and it will be allowed to flow that way. Does that make sense to everybody before we move on? Okay, so we're using a signal that we don't want to take current from, and we use that signal to produce a much larger output. Whether we care about current or voltage is up to us, but if you kind of think about some of the things we've looked at, like if we go all the way back to like the LC tank and stuff like that, then this is another application where it's like you don't want to take energy out of one system, but you can use the signals from that system to drive a much larger output. This is kind of similar to what we talked about with MOSFETs, but on a bigger scale, and you can have it go any direction you want, and as we'll see a little later on, has a lot more interesting applications. So going straight into the most basic uses, so I made this in LT Spice so I could actually get a waveform out of it, which means that it's a little more awkward to schematically represent. If you were to actually kind of doodle this, very quiet, so nobody can hide here. So usually if you were going to schematically draw this, you draw your little magic Dorito up. Conventions kind of vary, but oftentimes a lot of people will put the non-inverting terminal on top. And then you'll just say like plus Vs. In this case, 20 volts, plus 3 volts. You have your negative, so negative Vs minus 20 volts. Our inverting terminal is hooked up to ground. That is common for some applications, not so common for others. And our positive one is hooked up to a sine wave generator. So it is a 5 hertz, I believe. Yeah, 5 hertz, 50 millivolts. 5 hertz, 0.5 volts, we'll just call it. And then we have it feeding some. Most of the time for like an electrical purpose, you just kind of represent that via a resistor. You're saying, hey, it's doing work here, it is dissipating energy. That's effectively a resistor. We put it at 10 ohms for this one, but it's kind of irrelevant. And so a comparator, all it is doing is saying, which is higher, my inverting or my non-inverting, and whatever it is, I'm gonna output like the most of that I can, basically. Yeah, so in here you can see that the input signal, 50 millivolts, 5 hertz, it's taking this signal and everywhere in an ideal op amp, everywhere where it is above 0, it goes to max output and it stays there until you go below 0, and then as soon as you go below 0, it swaps to the negative output. Yeah, if you want to actually compare it against something, what you could do is instead of attaching this to ground, because basically we're comparing this against ground, you could put some other voltage in here. You could have a battery, right? Plus minus, and if this is at 30 millivolts, then, well, what do you guys think about it? If that's at 30 millivolts?
Wait, how much is going into the plus end?
50 millivolts.
50. Okay, so the gain would be like, you'd take 20 times the gain.
Yeah, and so for op amps, so for differential amplifiers, the gain is like a real number. For an ideal op amp, the gain is theoretically infinite. So, which is kind of why this goes, because if it just had a gain factor, it would be a multiplication of this. So, I should have better mentioned that. That's a good point. Yeah, but just assume that for op amps, they always just want to go as high as possible, basically, and as low as possible when required. But continue.
Oh, but like excess would be going from the plus terminal. There's more in the plus, so then it's gonna like output positive signal, right?
At what condition? When is it gonna output the positive?
Like at the peak, whenever it's higher than 30 like millivolts.
Exactly.
It'll go out like a positive.
Which the key there is whenever it's higher than 30.
Oh, because it's oscillating.
Exactly.
Right. Okay.
So if you can imagine this, it would be negative, 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 and as soon as the sine wave hits 30 millivolts, jump up, very narrow peak, and so like all of these peaks would narrow to just the points where this hits 30 millivolts. So it'd probably be, based on like the shape of sine wave, it'd be like, these would be like half the width. Well, okay, that's a nice convenient way of establishing like a square wave or rectangle wave technically, right, that is not the same sizes anymore. But it's also useful for if we weren't inputting a sine wave here, all we wanted to know is which of these two signals is higher. A comparator would be a great way to do that. Does anybody have any questions about that before we move on?
Why are the like Why is there little excess green lines?
Yeah, simulation. It's an ideal op-amp, so like part of it is just technically this thing responds like as fast as light and has some like
Okay.
it's not very real. So it has a little bit of overshoot during the transitions there, just because it's. We'll talk about some of the like differences between ideal and real op-amps. Probably not on the next circuit, but in a little bit.
Okay.
Okay. And comparators are also kind of great for like a binary system, right? Because if you're running a 5-volt binary system, this is a nice way to say yes or no, binary, 1 or 0. Next up is an amplifier. So this one does have gain. It's technically external to the op-amp because it's not using a differential amplifier, it's using an actual op-amp, but you set the gain exterior to it. So I'm going to draw this one on the board. So yeah, we're using very similar kind of like positive 20 volts, negative 20 volts for the supplies. We have, again, just a 10 ohm resistor on the output. But this time, and this is what is most common for op-amps, we have a feedback loop. So no longer is our negative, our inverting terminal just like either connected to ground or connected to something else. We are actively taking this circuit and saying, I want to do something based on the output of this circuit. So we have a very specific proportion here, which is to say, this is 19/20ths, and this is 1/20th of 10,000. The 10,000 is not important. The ratio is important. So we'll get to that in a little bit, I guess. But so we are taking the same signal, same AC wave, right? So another, the AC wave is the red one on here. Again, 50 millivolts, 5 hertz. And we have these two resistors, which 95 and 5. And this is just so basically, the difference between an ideal and a non-ideal op-amp that is relevant to us here is that non-ideal op-amps, real op-amps, they take a bit of time to transition. They are not instantaneous. They have what's called a slew rate. That slew rate is actually kind of very important for this. Basically, imagine starting from 0. This starts to rise some very slight amount. Based on what we talked about earlier, this is going to immediately want to just shoot up as high as it can. But as this voltage goes up, you're now establishing a path for current this way, which is why we have kind of high resistances here. Is because we don't want a lot of current going that way. But the current's not what's important. 1/20th of the voltage at this point will be detected right here. So everybody understand that before? And you get why? So because we have a voltage divider, which we talked about in our very first workshop, we are establishing this voltage as 1/20th. So still kind of working on the we're, from an individual time point, consider that this op-amp, even though it is real and it is operating, less than infinitely fast, it is still much, 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 much slower than a 5 hertz sine wave. So we're still at that initial, t 1 over infinitely past t. Like we are a millionth, a billionth, a trillionth of a second past it. And as the voltage is going up and up and up and up and up, this voltage is going to keep going up. And when do you guys think it's going to stop? When do you think it's going to stop raising voltage? If we're thinking back to that original valve, when is it going to stop moving its little hydraulic port?
Like when they're equal, right?
When they're equal. Does everybody understand that? So, right? The condition for not having our little hydraulic valve moving anymore is the pressures are equal on each side. Right? That makes sense? So, this thing is just gonna try to go up and up and up and up and up until 1/20th of this voltage is felt here. So our output at that moment is 20 times the voltage of this input. And we can see that by going and waiting until we get to the peak. So we see same 50 millivolt input. We get to 50 millivolts, 20 times that, 1 volt output, which is kind of crazy, right? Like this is, people, it's a little, you look at like all the ways they teach you about op-amps, they're always like, they have infinite gain, you can just make energy out of thin air. And it's like, well, no, if I tried to amplify it more than Vs, it would stop at Vs, which we'll explore that later. I often feel like people teach it in a weird way, because half the time people would just not draw these supplies. You'll just be like, yeah, you just have infinite voltage, and you're just generating power, man, from nowhere. And it gets you the ideas and lets you do some mathematical operation and calculations, but it really, like when you start to go try to make something out of op-amps, you go, what? I have 2 extra terminals, what are these? But you can see, because we specifically hooked it up with like our input voltage to the positive and our feedback to the negative, we are just multiplying with a gain of 20 in this case, our input signal. If we swapped these 2 terminals, if our feedback went to our positive terminal and our input went to our negative terminal, what do you guys think would happen? Any guesses?
We just,
You've already talked too much. I want someone else. Someone else needs to say it. Come on, guys. This is a low hazard environment. I'm not gonna kill
It
you.
would slowly go down as the other one started to gain.
So what would like the overall end signal look like? Would it look the same as it is now, do you think?
No, it would be opposite of what
Exactly.
it was.
Exactly. So if we decided to go to the inverting terminal instead of the non-inverting terminal and apply the feedback to the other side, it would be reversed. So like if we wanted to flip the sine wave while we were doing this, that's something we could do. Does everybody get that before we move on? This is like a very convenient way to do amplification. Everything else we had earlier was like a lot more of like trying to figure out signals, and like you would have to change your capacitors and inductors every time, and like a bunch of careful stuff around transistors where you have to worry about a lot of stuff. And this is like honestly pretty low sweat. You can just say, I don't care how fast it's coming in. I don't really care how big it is, as long as it doesn't exceed my supply voltages. But like kind of the only parameters you really care about are like output current and the maximum you can supply to it. So next we're going to move on to a summing op-amp. So they're called operational amplifiers because they do mathematical operations. This is one of the easier ones to do. And this second op-amp, you just kind of ignore this second one. This is literally just here to make it positive. If you look at most of these operational amplifier configurations, almost all of them invert the signal while they're doing it, and I didn't want to have that for this one, at least the first one, because it would just make it more difficult on us. But this is a summing op-amp. This does basic addition for us. So again, this would probably be a little bit easier if I kind of write it on the board, and then just like have a box that says flip the signal, I guess. But yeah, still using, there's a random ground there, ignore that, I just didn't delete it for some reason. Plus, that's not where the plus goes. So in this case, yeah, we have our positive terminal going ground, which for the sake of convenience, I'm gonna flip these again. Negative, positive, ground. We have negative Vs at negative 20, we have plus Vs at plus 20, we have our same 10 ohm resistor on the output. That is, yeah, and I should probably be a little bit more clear about what we're measuring in some of these, because 90% of the time we're measuring the inputs and the voltage from like here across this resistor basically. And there is a box that says flip. Yeah, flip, whatever. That part doesn't really matter. But we have our feedback coming back. We have a 10k ohm resistor here. This 10k ohm is, once again, so 10,000 ohms. This is again important for setting the gain. The gain in this case is set by these resistors and that resistor. They should all be the same if you want the gain to be 1, right? But so coming off of here, we have 3 different voltage supplies, each with a 10 ohm resistor in front to equally balance them. You could theoretically, if you want to, like, if I wanted to multiply this by 2, I think I would divide this by 2, I think is the way it works. But I didn't actually double check that beforehand. And so for this, the top one is a sine wave again, and this one is 5 hertz. Oh, I'm ready for 5 hertz, 2 volt peak to peak. Peak to peak meaning it is centered on 0. It's going 1 volt up, 1 volt down. 2 volt peak to peak, right? The middle one is just a 5 volts DC supply, so it's literally just 5 volts. And the last one is a very slow triangle wave. So we talked a little bit about wave shaping early on with the inductors and capacitors. I don't know if we've explicitly gone through and talked about these completely, but I think it's also this 5 hertz triangle wave. There's like 3 basic types of waves, right? There's your basic sine wave, there are triangle waves, and there are square and rectangle waves, which we covered a little bit earlier today. So this one's a little bit less obvious to explain. I think it might be easier just to discuss the output and not worry about how this one works too much. But we can see our, I guess it's more than 2 volts peak to peak. Oh, sorry, it's 2 hertz, 5 volts peak to peak. I mixed those two up. So we can see our AC input here, 2 hertz, 5 volts peak to peak, so it goes up to 2.5 and down to negative 2.5. We have, wait, is it 5 volts? I guess it's 5 volts amplitude, 5 volts amplitude. Okay, I'm sorry, I'm doing so dumb right now. But 5 volts amplitude, so 10 volts peak to peak. Then we have our DC 5 volts, which is just gonna lift everything up. Finally, we have our very slow triangle wave. Our output is this kind of orangish brown line. So it's taking all 3 of these. Like the kind of like the boring version of this is you literally just take like a 5 volt DC, a 3 volt DC, 2 volt DC, and you get 10 volts out, right? That's the easy, kind of boring one. And I thought I would hopefully not confuse you guys by saying we don't have to just sum DC. We can sum wacky stuff. Our output here is like, it's biased, right? So it goes all the way at the 5 volts. Actually, is it summing the DC component? It almost doesn't look like it is. But you can at least very clearly see the sum of the sine and the triangle wave, right? We have a sinusoid, but it's following this. It almost looks like it's not doing the DC, and I don't know why that would be. It might just be a glitch in the in like running the application, but sometimes the software gets a little weird. But so like if you wanted to sum a few things, which we'll show this a little bit later. Can anyone think of like any immediate reasons to use this? Maybe thinking a little bit about the binary stuff that we've talked about before, and like what's that?
Because you could have like a temporary really high voltage that would switch the binary on for a sec, and then it could oscillate down and then turn it back off again.
Maybe. We'll talk about some use of this later. Not quite what I was thinking, but that's certainly a thing you could do with it. Or it's kind of one of those things where it's like, it is one of those things where it's a little difficult to just on the spot be like, oh, I need to add these things together. But it gets used. So this one is an integrating op-amp. I did not bother to uninvert it this time, which is why the output you'll see is negative. But if we think about what an integral is, this square wave, it goes from 0 to 1. I tried centering it on 0 because you can actually basically turn this into a triangle wave, because if you imagine it being centered on 0, the integration of a square wave would be going up, going up, going up, going down, going down, going down, going down, going up, going up, going up, going down, going down. Which is one of the purposes of an integrating op-amp, is making triangle waves. This is not using an ideal one, so you can actually see that this is not instantaneous anymore if you can really pick out the like 1 pixel like differences every now and then. Again, this one, the normal operation of this inverts it. The thing to notice here is that you have a capacitor in parallel with a resistor connected up to the negative terminal is generally how this works. A differentiating one, I think, has it in series. Yes, has it in series. But you can do differentiation as well. For those who haven't, I mean, I'm assuming here everyone's probably in calculus or taking calculus, but you like understand the basic principles, right? So if you care about the rate of change of something, for example, probably most of you haven't heard of, I bet the three of you guys have heard of proportional integration, like PID controllers, proportional integrating differential controllers. Yeah, that's, I figured that probably, surprised you've heard that actually. I figured probably a lot of people who haven't gone into control theory probably don't know much about it, but the PID controllers are an evolution of proportional controllers. The older version, which would basically take a difference, like we use proportional controllers on my submarine a lot for running heaters for spaces, right? You say, it's this cold, I want it to be here, I'm gonna put this much power through the heating coil, and that's gonna like heat the room up more. If it gets colder, I'm gonna apply even more energy, right? So, you take a difference, you amplify it, you proportionally control it. PID controllers are that proportionality, but also incorporating like integration and derivation using these circuits, right? So, using an integrating op-amp, we can get the integration portion of that, and using a differentiating op-amp, we can get the differential portion of that. So if we want to have our system be able to like respond really quickly, then we might reduce the integration. We'll have the integration portion of it build up slowly. So then it'll immediately, like if there's a proportional difference, then it will respond to it instantaneously, while the proportional signal slowly builds up to like cancel it out and drag it back to 0. What's up? Gotcha. And so if we have both of these in combination, we can use that for control systems. Basically, like if you had a differentiating op-amp, then you can use that to say like, well, we're going to use that to like tell it not to go up so fast. Where if it has a high rate, it can say, oh, I want to change from this point to this point slower. Which for like dynamic operations is very important. This is used for like stuff like autopilots and stuff like that, where it's like, I've changed my flap a tiny degree, you know, I'm getting this much lift, my heading is this, I know I need to be over here, but what you don't want to do is have a system which is going flap here, flap here, flap here, flap here, and just instantly changing back and forth. So like your integrating signal, if you had the integrating portion of that high, this continues to build up if you're like oscillating kind of about one point, and will provide like a negative feedback to say like, okay, maybe stop switching back and forth between these 2 points a million times, and like causing the aircraft to go woo. And it says, great, maybe you should like chill out and find a place in the middle of that. This can also be used for timing. If you want it, like imagine applying a DC voltage to this, right? If you apply a 5 volts thing to it, then it's going to, based on the capacitor and the resistor and time constants, which you know you can look up those formulas on your own, not important to learning about the tools of today. You can say, hey, right, like I'll do it somewhere where the camera can actually see, I suppose. The integral of this is this, right? If we just assume like, you know, 0 for the top graph, 0 for the bottom graph. The integral is this, right? So if you want 5 seconds after this signal, like if this signal's been here for 5 seconds, then you can use that and say like, I want to trigger 5 seconds afterwards, or 4 seconds or 3 seconds. By having an integrating op-amp slowly building up some voltage, and when it hits some other voltage, you have this connected to another, you have it connected to a comparator, right? You wait until this reaches 3 volts, and then it's hooked up to another little comparator, and this goes, oh, we're at 3 volts now, I'm gonna say yes, right? So like, you can really chain these things together to do impressive things. Does everybody feel like they understand the basics of this before we move on? Okay, so I didn't show a differentiating one, but it's very similar, and the same kind of processes are kind of there. And like I said, for the basic uses is building up the signal over time. So this is very good for like time delay signals. Another application is our old power supply. The basic uses are none because it doesn't kind of work. Technically, it does work, but not if you put it in parallel, which is where I went wrong. So this kind of pulls on all of our lessons. Does anybody, we're gonna start with like the very, well, typically this goes on diodes. So yeah, we'll say from our first two lessons, can anybody describe to me kind of what, we have a DC power supply, we have this resistor, we have another resistor, and we have this diode that maybe somebody remembers the name of. Does anybody remember what this is called?
Hotkey.
Nope.
Is it the Zener?
That is a Zener diode. Do you remember what Zener diodes are used for? Anybody? Why is it pointing the wrong direction? Does anybody remember that?
Oh, it's the inverse one. Like it flows the opposite direction.
And why does it go the opposite way? There's a very specific purpose for it.
You wanna make sure that you get 5 volts at least.
You want to make sure you get 5 volts. So a resistor, the voltage drop across a resistor will vary with current. Zener diodes, if you guys recall, are very useful because they will always drop the same voltage regardless of the current until you explode it. So we have, now what's the purpose of this resistor, right? If this is already giving us 5 volts, why do we have another resistor here? Think back to what the main uses of a resistor are for.
Is it limiting current?
Limiting current. So we don't want to send like 500 amps through this thing. So we have a moderately sized resistor, not huge, not small, chained up to this Zener diode. Now with what we just talked about with the OpAmps, right? We're taking that 5 volts that we just talked about, we're sending it to the non-inverting terminal. And then we have the inverting terminal hooked up to the output, and our supply voltages are the battery and ground. So, you know, the supply voltage to the battery to the ground, right? Like we don't care about the negative voltage, there's never gonna be a negative signal. But what is happening here, we're sending 5 volts here, and the feedback is coming to the non-inverting terminal. Think about how I first described that sine wave, that amplifier. Do you have an idea?
It's going to slowly build up until it matches the input.
Perfect, that is exactly it. This is what is called a voltage follower, because it follows the input voltage on the non-inverting terminal. So we're developing 5 volts here, we're applying it here and saying this will always be 5 volts, right? The battery is not always 5 volts. We haven't talked too much about batteries, but like battery voltages do this, you know, they start at a really high voltage when they're fully charged and they drop off. And if you have a high precision system which needs better, more stable voltage than that, that's not what you want. So we are taking that and we're saying, great, we are now just outputting 5 volts. All right, what about the very last part? Does anybody remember some of the basic uses of inductors and capacitors and have any guesses on what we have this for? Miles, do you have any ideas?
Just cleaning up the signal.
Yeah, I mean, there's a specific word for it that's actually in all the names of the components.
Oh yeah, it's a filter.
It is a filter. So we are filtering out components. We're making it nice and smooth. A filter in signals processing is either like a low pass filter, a high pass filter, a band pass filter. A low pass filter passes low frequencies. A high pass filter passes high frequencies. The only frequency we want is DC. So we're trying to get like the lowest of low pass filters. This filter basically just says, if it ain't DC, I don't want it. If you're changing anything, don't. So, and we do that through, like we talked about, 2 different methods of storing energy. Storing energy through voltage and storing energy in the form of like current, or taking current and storing energy and taking voltage and storing energy. Because this is just one, so right, I couldn't actually find any OpAmps that I like the voltage settings on. I think I can go back and actually just find a better one maybe. I don't know why, but there's, like most OpAmps are for very small voltage, very small current applications, and very unfortunately for us, there's a weird gap between power OpAmps and most OpAmps where we're in a very not ideal region for apparently manufacturers. They don't want to bother to make anything that we wanted. So I tried to put 3 of these in parallel, and it turns out if you put the feedback to each one of these and connect them all together, because you want all their current coming together, then you get the feedback from each of them to all of them, and they get really unhappy, and then they get really, really hot. So that is the current problem with our power supply, and I think now you all understand our previous power supply, hopefully, and maybe what was wrong with it, right? So if all of them are feeding back to each other, the highest voltage wins, and it gets really unhappy. Does anybody have any, well, yeah, I guess I'll talk a little bit about the graph. So all of our previous graphs were over time, right? This one is not. This is sweeping a voltage, simulating our DC battery slowly dying, basically. Starting at 8.2 volts, I think it is, or 8.4 volts, and going down to like about 5.0. So we're saying, like, if the battery changes, how's our output? And we see that our output voltage is pretty stable around 5 volts the whole way across, which is exactly what we're kind of looking for. It has a very small, what is called droop, which is more of a load sharing characteristic term, but it still kind of applies here. So there's a slight droop. In reality, we got like exactly 5 volts, so it might be one of those cases where the real case was a little bit better than ideal. Yeah. Any questions before we move on?
Wait, what's the red line?
The red line is the battery voltage.
Oh, okay.
So red line is battery voltage, green line is the output of our system at 5 volts. But it's still drawing from the battery, which is the important part here. So we're still using the battery's power, right? Because it is now our supply voltage. But this is saying, you know, oh, you're 8 volts, I don't care, you're 5 volts. You're 7 volts, I don't care, you're 5 volts. You're 6 volts, I don't care, you're 5 volts. And damn, I don't think we actually talked about this. Well, no, yeah, you guys remember the boost converter, right? Step up voltages?
Right.
There's another name for boost converters called joule thieves. They steal energy. They're used, if we wanted 7 volts and this was below it, you would have a boost converter to say, well, screw you, you're not 4 volts, you're 5 volts, because you want to pull every last bit of energy out of this. We have our 2 in series wired into here, which is why it's a higher voltage than it would be otherwise, but even when they're dead, it's still above 5 volts, so we wouldn't need something like that. Just why I chose 2 in series actually just simplifies the system. Okay, any other questions? All right, this one is a little bit more complicated. We're not going to go too deep into the details, but this is making a basic oscillator. This one's a little bit interesting because I have an input connected here. It is chopped off because this system requires no input in real life. It's actually kind of crazy. We won't go too deep into exactly how. Is there any spray? Probably not. Okay, I guess. Just push harder. So here you can see we have feedback. This time, this is not, this is setting the sine wave's peak right here. So you can see right here, there's a 2-to-1 relationship. We end up with a 2 volt sine wave. These 2 sets of capacitors and resistors are setting the frequency of it through a way that we're not going to explore right now, again, because that's finding time constants and finding the actual frequencies is a little less important here. But the important things to know here are your feedback is actually connected both to the inverting and non-inverting terminals. So yeah, we'll draw plus on top of it, I guess. So you have a purely resistive feedback to this one, which is being used to set the voltage of the sine wave. But the feedback to the non-inverting terminal is not purely resistive. You have a capacitor in it. The capacitor, like we talked about, is going to take some time to charge up and discharge. So this represents sort of a delaying function to it. In addition to that, off to the side here, we have in parallel. And it's not too important that you remember the exact instruction here. It's mostly the purpose and kind of why it happens-ish. But you have something setting timing, something else setting timing, and you have your gain, sort of. Now, in this circuit, because I was using ideal components, I had to kick this off with a small little pulse that I didn't bother graph, and I just make sure everything went backwards. In real life, we are sort of lucky in that there's just magnetic fields everywhere, and things just sort of happen. So this will actually self-initiate into this operation. But what you'll see is there is a large transient at the beginning. The input pulse of this was a 0.0001 half a millivolt impulse. And even that is more than necessary. And the impulse has zero zero impact on why this went up as high as it did. This is completely determined by the system for the first pulse. And what we see is we see a little bit of an adjustment period, and then we see a very, very nice sine wave after some number of seconds. Since I used a relatively large capacitor and resistors here, our time constant for this is 1 second. And anybody who knows a little bit about how long you expect it to take to get to steady state with different systems, it's about 5 time constants. You'll see this goes through 1 sine wave in about 5 time constants, a little bit larger. But again, less important. There are equations for this that can be found in Wikipedia and in textbooks and stuff. But the important thing to know is hey, we've used an op amp and we just made a sine wave. And it might not make complete sense how we did it, but again, this workshop is mostly about the tools in your workbooks. What's up?
How is that possible to create energy for an atom?
Oh, well, again, this is not creating energy. The energy is coming from your V supply. So we don't have an initiating signal to it, but we still have our plus Vs and our minus Vs.
Okay.
Plus Vs and minus Vs is where your actual power is coming from.
Okay.
This is just for sensing and determining the output. So the output is determined by the signals you send to it, but the power comes from your supplies.
Okay.
And in real life, there's the ideal diode that has infinite current output potential and infinite voltage supplies. And that's a little silly. In real life, you'll have a voltage and current rating assigned to the op amp, at which you'll say, okay, I can only do 1 amp, which is the case for ours. There will be bands in which you can only have these voltages be 20 volts apart, or no more than 10, or no more than 10 millivolts in some cases, or smaller. But yeah. But remember back again to kind of what we said in the very first lecture. A lot of inductors and capacitors is used for timing and wave shaping. And so when you see inductors and capacitors being used in weird ways, you should think all right, this is probably being used to either delay a signal, or it's used if you're dealing with AC, then passing AC through one of these will either completely get rid of it if it's too high a frequency, completely get rid of it if it's too low a frequency. Yeah. Or it will phase shift it by half a pi or pi, depending on what you're doing. And that's dependent on the angular frequency. But okay. Any other questions before we move on to our next example? All right, cool. Yeah, so it's really cool that we can just make our own sine waves out of DC. That's a good thing that you should be aware of. This is a 555 timer. These are extremely common. So these can do a lot of things. We mentioned flip-flops in the transistor workshop thing, because a flip-flop is basically kind of a logical operation, but you should think of it like a bistable. And remember that a bistable is something that has 2 stable states, and you can cause it to go between them, which is the R and the S and the reset. There's more to it, and the particulars are not important. If you ever look up, you can Google what a flip-flop is and look at the Wikipedia page for it. But you'll see we have 2 comparators here that we talked about a little earlier, and we have some sort of op-amp. At the end, so 2 comparators, op-amp. I didn't talk about this before, but this is the logical symbol for inversion. I think we briefly drew a transistor diagram of what that would look like, where it's basically if a signal is present, then do the opposite of that, short at the ground with a bipolar junction transistor. But if we're thinking about logical systems, once again, think of this as 1 comes in, 0 comes out. That's all you really need to know about that. And you can see that this is an inverting op amp because it has that same symbol in front of it. And these, the smaller circles are just terminals, so we're not inverting every single signal. Like I said earlier, VCC is a common digital supply thing for saying hey, we're supplying voltages. In this case, it's being used in a voltage divider, which is going to have a role in this timer's frequency of operations. I don't think we need to go into too much detail here. Just know that the important thing here is it voltage controlled oscillators. You can use them to make square waves. You can use them to make triangle waves, I think, question mark. I don't think they make side waves. I probably should look at it a little bit more. But this is, these things are like very common in terms of like using a couple of OpAmps to do one thing. You can usually just buy these as an IC, integrated circuit chip. And I believe this is actually what John Davies initially recommended for our power supply, but because they're voltage dependent, I was not a fan of that because then the battery voltage changes. So he might have been thinking of something else, but everything I tried in LT Spice, our simulation software, was just like not great. So I don't really know what he was going for with that. I might come back to it, but I will not take questions on this because you don't need to know much. Just know that 555 timers exist. So this is just kind of blanket advanced uses. So I didn't want to take a picture and put them in for each one of these because there's a whole bunch of them. But this is what I was getting at with a summing op amp, digital to analog converter. So think about summing a bunch of digital signals. If you have a bunch of like binary ones and binary zeros, then you can take all of those ones and say, great, that is now like some analog signal. Which is to say, like, if you imagine sending in like a 4-bit system, right? Four bits, so 1, 2, 3, 4 supplies, and you send in something like, you send in, we'll go with 0, 1, 1, 1, we'll stop there, and 0, 0, 1, 1, 0, 0, 0, 1, and 0, 0, 0, 0. If you feed those to a summing op amp, that's not a triangle. You know, we're just gonna make this very simple and just connect them like this, but those resistors still need to be there. You feed them into a summing op amp, your output voltage over time, with each increment being however long your clock speed is, right? So at the very first clock impulse, you see 0, 0, 0, 0. It sums them. We're gonna call 0 right here. It sums those for the very first clock input. For the second clock input, you see 0, 0, 0, 1. Okay? We have whatever logical one is for this. This is now 5 volts if it's a 5 volt system. It's 2.5 volts if it's a 2.5 system. Now we've got 0, 0, 1, 2. Sorry, 0, 0, 1, 2. 2 times. I need to go down. For the third one, you have 0, 1, 1, 1. Now we have 4 times. Well, if you have this in incredibly tiny amounts, say like instead of 4 bits, we're talking 256 bits, and if you control the timing correctly, I still need to be over here, I guess, you can have incredibly tiny steps going up and up and up and up and up and up and up, and then down and down and down. And then you take a filter, and it gets a lot smoother. But most of the times, you can make these tiny steps so small that it doesn't matter. So you can use an analog and digital converter to like turn things, and you can make sound waves this way, that you can control the frequency of using the clock speed and stuff like that, or by varying like what the order of these digits that are coming in is. You can use it to do other ones where it's like, you know, oh, I have 2 positive signals here, I'm gonna sum them, and that means it's 5 volts out, stuff like that. So you can do stuff related to that kind of using analog and digital converters, or digital to analog converters. And the reverse is true too, so analog to digital converters. Now we want binary digits from our analog data. So this is going back to like comparators, right? So if you have a whole bunch of different comparators that are set to, this is basically the reverse operation of what we just did. But imagine we have 4 comparators. You know, they're not hooked up to any sort of feedback. All they're doing is comparing in and out. You've got negative, 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 positive, 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 positive. You've got 4 volts, 3 volts, 2 volts, 1 volt, and all of the non-inverting terminals are hooked up to like something, V signal. So we're gonna say V signal over time, and we're gonna have V out. We're gonna, well, no, we don't want those connected together actually. So actually, yeah, V out doesn't make sense in this case. But we're gonna have something reading the outputs of these, right? Which we haven't talked about what can read these yet. But so let's say you got your input signal, and it looks like this, and this is a peak of 5 volts. You know, at this point right here, at 1 volt, you know, typically 1.001, right? We're gonna have, compared to this 1 volt, this will go positive, and this will output like a logical 1. This is too low, this is too low, this is too low. So we have 1, 0, 0, 0. All right, keep increasing. Now we're up to 2 volts. Okay, we're over this threshold now. So now we have logical 1, logical 1, logical 0, logical 0. So the output, so first output from T1 to 2. At T1 we have, depending on how you arrange these, but let's say we're going from here to here, we have 0, 0, 0, 1. T2, we have 0, 0, 1, 1. T3, so now we're going to be up to 3 volts. At T3, 1, 1, 1, 0. So we're going to write that 0, 1, 1. For the 4th time at which it reaches 4 volts, they're all on. So it's 1, 1, 1, 1. And using some system, right, you might have some use of this information depending on what you're trying to do. But like you can have that drive some sort of output, do whatever you want. You can use Boolean, you can use those, we talked briefly about like OR gates, AND gates, NOR gates. Use those to say, well, okay, once these 3 are 1s, I have an AND gate, right? So all of them have to be 1s for it to be 1. And as soon as all 3 is 1, it outputs a 1. And now we do work, right? So, you know, if we said, oh, I have a sine wave input, I want to turn on a fan, an LED, a whatever at 3 volts, this is the way to do that. Everybody makes sense of that? So I know I'm throwing a lot at you right now because like and we haven't talked too much about digital stuff, and I recognize that. But this is showing you like you can start to go in and out of the digital world and going back to the analog world very easily through these processes. There's sampling and holding circuits, or the more complicated versions of these are registers. But if you imagine an op-amp that is just connected to like a capacitor, like an ideal capacitor on its non-inverting, and then think back to the voltage follower. What if you have some signal and you just like, oh, I want to check this signal right now, and for like a millisecond you apply it, and now that signal is just locked here on top of that capacitor and constantly outputting that signal. So you can use this to like sample at a specific time, like saying like, I want to check my resistance temperature detector so I can check my temperature. I'm going to check it right now, but I don't want to calculate it or do anything with it until later. Or maybe I want to store it for some reason to do something else with it later. Then you can just very briefly stick that signal, which, you know, theoretically, right, you don't want to have it constantly going and like pulling current through the system. So you can very temporarily sample something and hold it. Yeah, and you can draw basically like you could have this being gated by a MOSFET, kind of once again linking everything together. And everything we've talked about, a lot of the stuff we talked about before, you can do with OpAmps. You can do clippers, right? If your voltage supply stops at 5 volts, you can take a signal that goes above 5 volts, and it's not going to be more than 5 volts. So you can still do clippers. You can do rectifiers by flipping things, causing them only to go at certain points. Using comparators and stuff like that. You can do filtering operations in like a very similar way. These, in some ways, are better filters because we never went into this because it's beyond the scope, but induction capacitors phase shift things, right? If you send an ADC sine wave through a capacitor or inductor, it comes out like shifted left or right, which can be annoying, so these can avoid that. You can make triangle wave generators, kind of like we talked about. You can make square wave generators, 555 timers. Almost like everything is OpAmps these days. It's all OpAmps the whole way down. So, and that kind of wraps things up. Does anybody have any questions? I need to leave soon. But I could be late to that a little bit, so if you do have questions, don't feel afraid to ask. So I'm pretty sure it's the last slide. Yeah, it's the last slide. Okay. So, things to remember about OpAmps. Part of their purpose is in the name. They amplify. You can use them to do very direct comparisons to say, is this higher, is this not higher? You can do voltage followers to just follow the output, whatever you're doing. You can do math with them you can find integration. You can do integration, do differentiation. You can sum, you can subtract, stuff like that. You can use them for kind of everything we've already talked about. And really what should probably stick in your head the most is you can take a signal and not using power from that signal, drive another power source to do what you want with it. And that has a bunch of kind of wonderful and insane different applications depending on how you wire things up. So the op-amps in our circuit were these ones right here. The problem is there are 3 of them, which is why it doesn't work. So, all right, well, thank you everybody for coming. I'm still kind of mulling over what the next workshop is going to be on. I'm thinking about maybe doing something on binary and Boolean algebra, which is using all those OR and AND gates. Are you guys familiar?
Oh,
Yeah. I kind of like Boolean algebra. I don't know, but it's either gonna be that or I'm just gonna I've also considered. Well, it's also Friday right before fall break. Who else is gonna be here next week? Do you think? You guys think you'll be here? Yeah, it's understandable if you're not. It's literally like the Friday before fall break. So, but yeah. So it's either gonna be like logic and Boolean algebra for digital circuits, or we might go into like starting to look at things that we're going to need for our CubeSat. So we might look at like a power supply ideas for a boost converter. And like slightly more practical things where we start saying like, okay, how do we actually calculate these things for duty cycles? Or we might look at like a temperature detector in case we want to know the temperature inside of our thing. But that's it. So, wow, yeah.